Awesome. So I'm gonna see if I can get my screen shared up. All right. We're going to be talking today about exploring modeling assumptions with census data, and we're going to be using census data from the United States and Guatemala. And I just want to share that this was originally from a student project in class. We would do a project with census data. It was actually in a senior level mathematical modeling class. We would do all of our initial analysis with the United States data, and then would send students off to get a data set that interested them, so that there was something that they were doing that was a little bit different, and basically redo all of that analysis. Gary chose Guatemala, which was an interesting choice from a number of standpoints, starting with the fact that there was not actually a nice record with the data. So Gary started out by spending a lot of time getting this data together. It's now available on Guatemala's Wikipedia page. It's also available with my Simiode module, so you can get it in either place. And that reminds me, I was going to, whoops, I'm going to lose my view of the screen here, I think, but that's okay. I can deal with this. I was going to share with you some resources I had on this. So let me get a link to put in the chat. Okay. Okay, and copy link. And now I am going to shrink that out, and can I get my main window back with my view of what we're looking at? I hope we're still looking at the slides. And can I find the chat window? Of course, it's always complicated because Zoom starts hiding things from you. So I'm putting a link to a Google document in the chat, and that should bring you to some resources that go along with this talk. All righty. So Gary had to first get the data. The data is with the Wikipedia page. I am on native land today, by the way. I'm on the land of the Yakima people, and I want to pay my respects to the Yakima people and for all they've done to preserve the land and the water that support all the people on this land. So let's take a look at the United States Census data. I have not included the full table here simply because we don't have enough space. It's easy to get. You can find it on Wikipedia and other places. There are references certainly in my paper about this. I'm pretty sure a Google search will get it to you. If you graph it, it looks like this. Now, if you're thinking in terms of mathematics, if you want to think like your students do in a calculus class, maybe they're a beginning differential equation student. If you show them this data and say, what function does this look like? I want you to think for a second, what answers would come out for you? What do you think they would answer for you? The Guatemala data is a little bit rougher. We've got a table. This is the full table here. I've got a plot for it here. You will notice that the general trend of the shape is very similar to what you see in the United States. There are a couple of more wobbles in this data. It goes up and down a little bit more. It looks like it's got a little bit more noise in it. Guatemala has an interesting history with their census, and there's definitely reasons in certain cases to question some of the numbers that are in the Guatemala census. But I actually want to note that that's also true with the United States Census. I mean, this last census that we took in 2020, you might recall that the president at the time was very much pushing the Census Bureau to get done. We were in the middle of a pandemic. People didn't feel like they were done. And so if you look at the relative errors of this 2020 data versus the 2010 data, you'll find that there's a lot more error in the United States data than in 2020 than say in 2010. And you'll learn that there are some shocking systematic errors in the United States data as well. So I just wanted to note that all this data can be questioned in some sense, but it is nonetheless the best that they have. So one of the things I asked you to think about is what kind of general functions do you think your students might mention if they asked what shape this was in? Anybody willing to shout out or type an answer in the chat for that? So I see an exponential answer. I think that's the first answer many of us would come up with. And indeed, the exponential model is one of the models that's commonly used with populations like this. You've got kind of a general graph of an exponential curve in blue right here. Another common answer is the logistic model, and the logistic model is the black dots that are right here. One of the major differences between the exponential and the logistic model is that the exponential model keeps growing, whereas the logistic model, you can see it's kind of topping off. and it's going to go to a horizontal asymptote at what's called the carrying capacity. So I think we would say that these two graphs do look like the graph of the United States Census data and the Guatemala census data, but not always. And I would like you to think for just a minute, how do these graphs, either the exponential or the logistic graphs you see here, how do those differ from the data? So I'm going to give you just a minute to think about that. And I'm going to go back and just remember what this picture looks like. Let's go look at the data again. There's our Guatemala data. There's our United States data. In particular, could anybody think of a way in which the logistic model differs from the data that you just saw? And I am hoping you're all sitting there thinking to yourself, the logistic model is really kind of leveling off here. And I don't think that we're seeing this leveling off behavior really clearly with either the Guatemala data or the United States data. Maybe a little more with the United States, maybe that's a little bit of leveling going off right there. And maybe there's a little bit with Guatemala, but it's not clear that either of these two graphs are leveling off. So one reason I want to bring this up is that when we talk to students, often the first reason that they think a model is a good model to use with a certain data set is because that function looks like the data. And that's a reasonable place to start, but that's not usually what we want to have when we're building a mathematical model. We actually want to capture something else. So these two models, I think, are reasonably appropriate based on shape. And I do want to also point out one more thing before I leave the slide. The exponential and the logistic model are very similar down in this area of the graph. And it's just as we continue, eventually the logistic model changes and departs from the exponential model. So from a shape standpoint, I think both of these models, certainly they have features in common with our data. So that seems like they are reasonable choices. But when we talk about modeling assumptions, we really want to capture something about the physics of what's going on or the mechanism of what's going on. So when we're talking about modeling assumptions, the big thing we want to do is we want to simplify. We don't want to take everything that's going on with population into account because that's a lot of stuff. We want to simplify it and we want to capture the main physics of what's going on. So when we look at the exponential model, I'm going to look primarily at this differential equation formulation. So that is that the derivative, P of course is population, T is time. The derivative of population with respect to time is equal to R, which is a constant times the population. Now right here, I have what's called an initial condition for the differential equation. I'm saying that at whatever I'm going to call time 0, I know the initial population. And of course, if you know differential equations, you can integrate this model to get then this solution for it. If you're in a calculus class and you're talking about this, you don't need to go through how to get the solution. I would just start talking from this point. The exponential model from its foundation is really this one, that the change in population with respect to time is equal to a constant times the population. Now let's talk about what physics or mechanism that this gets. It's the rate of change of the population is directly proportional to the size of the population. And that captures the following idea. If you have a population of 100 people, and it has 2 births and 1 death in a year, what do we expect will happen to the births and deaths for a population of 1,000 people in a year? And I think that if you're thinking about this for a minute, if you think about what your students would be thinking, you would be unsurprised to have your students answer to you that with 1,000 people instead of 100, we would expect to have 20 births and 10 deaths in the course of a year. And this is exactly the idea that the number of births and the number of deaths are proportional to the actual size of the population. So when we have 20 births and 10 deaths, our total change is to add 10 people a year. So in this model, we would have R is equal to 0.01. So if the population size is 1,000 with R equal to 0.01, that change would be captured by this differential equation. And that's the big thing that we're capturing in the exponential model. Now let's do a little critical thinking about the exponential model. Is this actually true? So do you expect that same proportionality constant R to work with populations in every historical era? And do you expect that same proportionality constant R to work with every human population across the globe? Now, I'm pretty sure that you are already thinking, no, that's not really going to work. One example we can take with our recent COVID-19 pandemic, we're seeing a lot more deaths than we did before the pandemic. And that changes that's going to change this proportionality constant in order to drive the increase in the population down, possibly even decrease a population. So historical events like a COVID-19 pandemic, a war. Now I'm thinking of things that are driving up the death rate, that could definitely affect that constant. Another thing that could affect it is our medical ability. So there are a lot more children that survive into adulthood now than used to. And the fact that we have more children surviving would increase that constant R. And likewise, we don't expect that same proportionality constant to work for every human population across the globe. One thing that we've been hearing about in the news for several years is decreasing births in Europe. Many European civilizations have very low births, whereas many African civilizations, I believe African countries, Nigeria, I think has a very high birth rate. So we don't expect that constant to actually really be a constant, but approximating it as a constant is a first simplification of this model. This is a very simple model for population, and it captures one aspect of how populations change and grow. Doesn't capture them all, and we don't expect it to. So now let's take a look at the logistic model. So we would like to, again, simplify and capture some of the physics of how population change. So let's talk about how we get the logistic model. The logistic model includes a second cause of deaths. So in the exponential model, we're assuming that both births and deaths are proportional to the original population. In the logistic model, we assume that we have some other deaths, and those are from two-person interactions. Now, when we think of two-person interactions, you might think of one person coming up and actually really interacting with another. And certainly a two-person interaction that causes a murder or a fight that gets somebody killed, that certainly could be a cause of death. But there are a lot of two-person interactions that don't work like that at all. This also really captures the idea, the two-person interaction of a competition for resources. So if there is a limited amount of food, what food one person gets, another person can't get, and that might also cause deaths within your population. So what we want to do is we want to take that original exponential model and we want to add in these two-person interactions. So may I note that if there are P people in our population, then there are P possible choices for the first person, and there are P minus one possible choices to the second person. So the number of two-person interactions is P times P minus one. Technically, it would be over two because I don't care who it is that you chose first, but the number, a death rate that's proportional to the two-person interactions is going to be proportional to a term of the form of P times P minus one. And that's what you see here. dP dt is equal to A times P. That's an exponential term. And then we've added in the two-person interactions right here. And from here, we're going to just do a little bit of algebra in order to get this into kind of the standard form for the logistic model. So I'm going to multiply out this term right here. That gets me kp squared minus kp squared plus k times p. Now I'm going to collect those two p terms together. That gets me the a plus k times p, and then I still have that minus kp squared. So I'm going to factor out that a plus k and a p, and then I'm going to get this model. Notice I have a plus k times p, and then I have 1 minus k over a plus k times p. And now I'm going to rename. I'm going to call a plus k that's going to be equal to my R, and K over A plus K, that's going to be a 1 over equal to 1 over L. And this is then the standard form of the logistic model. Now, we've already said that the logistic model goes to a horizontal asymptote. That's the carrying capacity. Note that our carrying capacity in this equation is RL right there, as P goes from 0 up to L. P over L goes to 1, and we have then dp dt, the change in the population is equal to 0 when P is equal to L. So that's our kind of standard formulation for the logistic model. Now, I just want to note we've got the differential equation for our logistic model. We've got an initial condition if we're working with differential equations. I can get a solution for you. You would separate variables and then you use partial fractions here. If you're in a calculus class, you might not want to do that at this point. That's fine. I don't think you need it to kind of present some of these general ideas about modeling assumptions. Note that both the exponential and the logistic models are simplifications of a vastly more complicated reality. We're talking about human populations in the United States and in Guatemala. And I would encourage you to just think for a minute, or to have your students think at this point, what other factors influence the size of human populations like the United States or Guatemala that we have omitted from both of these models. So let's just think about that for a minute. Do any quick answers come to your mind when I ask you that question? Please feel free to type in the chat or shout out if something is coming to your mind. Nobody is super eager to share, and that's okay. But I'm hoping that maybe you had an answer that you weren't willing to share. The big thing that comes to my mind with this is I've talked about births and deaths quite a bit, but I haven't talked about things like immigration or emigration at all. So note that that's one big thing that I have omitted from the population change from these models. So there's certainly things that have not been captured at all here. So note that both the exponential model and the slightly more complicated logistic model are simple models, and they are real vast simplifications of a complicated reality. All right. So let's take a look at the modeling results with the United States data. Now, in my senior level class, we go ahead and we get all the parameters for these models. So we get a best fit model for the exponential and for the logistic. Part of the reason that I started working with census data was because I felt in a mathematical modeling class that we should do some parameter estimations. The United States data is kind of the poster child in this case. We get two really good models here, but here we can see that the logistic model, which is slightly more complicated than the exponential, really fits the data somewhat better. So in my senior class, when I was working with Gary with the Guatemala data, of course, he needed to go do this with the Guatemala data. So let's take a look at what happened there. So with the Guatemala data, note that I do have, in fact, on this graph, both an exponential and a logistic model, but I don't know that you can see that exponential model at all. Does anybody know where that exponential model is hiding? Well, that exponential model is hiding right underneath that logistic model. So we're basically seeing right here is that when we estimated the parameters, both the exponential and the logistic model got us the exact same parameters. Why is that? I mean, that seems pretty weird. The logistic model, you know, why is it getting the same thing? Now, I also want to note that we actually looked when we estimated that carrying capacity for Guatemala. We found that our estimate for the carrying capacity was 2.6 times 10 to the 8th plus or minus 1 times 10 to the 29th million people. So that is a gigantic estimate for the carrying capacity. Now, when we did the same thing for the United States data, by the way, the current population of the United States is about 330 million people. We found that that carrying capacity was about 500 million plus or minus 29 people for the United States. So let's take a look at the difference between those two estimates. This is about 500. This is 2.6 times 10 to the 8th, so that's huge. This error, 29, is substantially smaller than 500, whereas this error is a lot bigger than the original carrying capacity itself right there. That's, by the way, it's 1 standard deviation of error right there. So what this is telling us is that, okay, my computer has gone off. It has done the parameter estimation. It's saying when I'm estimating for Guatemala, I get a really crappy estimate for the carrying capacity. And my really crappy estimate is really, really big. So basically it's saying I'm having a problem doing this. Now we've talked about the modeling assumptions, and we would like to understand why is this estimate so crappy? So I'm going to go back to the modeling assumptions again to take a look at this. So something definitely went wrong when we tried to get the best fit parameters with Guatemala. We estimated an extremely high carrying capacity with an even more extreme error. And the logistic model was almost identical to our exponential model. And the question is, why is that and what's going on here? So to answer this, I'm going to go back to look closely at modeling assumptions and take a little bit of a mathematical look, pry into this to some things that were hidden from that original discussion that we had. All right, so the first thing I want to look at is a very common concept in population and census modeling. When we talk about changes in population, often you'll find people talking about per capita population growth or the per capita population growth rate. I'm going to call that PPGR. This is the growth rate that's averaged over the number of people in the population. So if we recall dPdt, that's the change in population with respect to time. If I want to average that per person, I'm just going to divide by the total number of people in the population. So if I want a definition, a mathematical definition for per capita population growth rate, the definition I'm going to give you is 1 over P dPdt right there. Now, note that I can tell you what the modeling assumptions are for both the exponential and the logistic model. This was my exponential model. dPdt is equal to R times P. So if on this left-hand side, I want 1 over P dPdt, that's like multiplying through on the whole thing by 1 over P. So here I get 1 over P dPdt is equal to R. So notice that the exponential model's assumption about the per capita population growth rate is that that per capita population growth rate should be constant. Now, if you do much modeling, that is in fact the simplest possible assumption you can have about anything, is to just assume that it's constant. So to some extent, we said that the exponential model was really a very simple, or the simplest population model. This again says, hey, this is a real simple model. It's assuming something is constant, and the thing it's assuming is the per capita population growth rate. Now, the logistic model, we've got the same structure for the equation. We've got dPdt equals. So if on this side, instead of dPdt, I want 1 over P dPdt, I'm just going to multiply through by 1 over P. So I get 1 over P dPdt is R times 1 minus P over L. So now what I'm going to do, this is my per capita population growth rate. I'm going to look at this side of the equation is the per capita population growth rate is a function of the population. And this formula as a function of a population gives me a line that is decreasing. I'm assuming that all the parameters here are positive. So I'm assuming R is positive and L is positive, usually is population growth. And what does this give me? Well, that gives me this. So the exponential model, we're assuming a constant PPGR. And in the logistic model, that PPGR is decreasing. It's equal to R when the population is 0, and it's going to be 0 when the population is L right there. Okay, now we know that this is what our model hypotheses are for these two models. May I note that PPGR, this formula, this can also be calculated from the data. And of course, let's go do that. Let's see what our data says about this PPGR. So most of our PPGR from our data, what we're going to think of in our data, notice I gave you years and I gave you populations. So I'm going to let I index these observations. So this is the first observation, the second, the third, the fourth, etc. So this right here, this would be T sub 4, and this would be P sub 4 right here. And I can, of course, use a forward difference or a central difference or a backward difference to approximate my derivative. So if I'm approximating that derivative, I would approximate it as P of T plus H minus P of T over H. And then if I want to get PPGR, which is 1 over P dP dt, I can approximate this as 1 over P sub I times the fraction P sub I plus 1 minus P sub I over T sub I plus 1 minus T sub I right there. You might, if you're teaching a class, whether it's a differential equation beginning differential equations or a calculus class, you might ask your students, give them the data, give them those graphs and ask them, how do you approximate the derivative from this data? How do you then approximate your PPGR, and see what formulas they come up with for this. And then you'll notice with these formulas, it is very easy to then do this calculation actually in a spreadsheet. So go ahead and if you have time in class to work with a spreadsheet, I would encourage it. I actually have been shocked at the number of my senior students or junior students who I ask them to do some simple calculation with this in a spreadsheet, and they look at me like the deer in the headlights. And it seems incredible to me that in the year 2022, students get to their junior and senior year in college, and they're so uncomfortable with spreadsheets that they can't do things like this, but it does happen. And this is the sort of thing we really want to get them to, or get them more comfortable with before they graduate, because that's a very common thing that we do on the job. All right, so let's take a look. Before we go on, note that if you go ahead and you plot your PPGR versus your population size, you might get a data cloud like this. Another thing you might ask your students before you actually send them loose with the spreadsheet is, you remember that the exponential model that got a constant PPGR that was modeled by a horizontal line in this data, and our logistic model was a line, a decreasing line in this data. How might you get those two things from data like this? And I'm just going to pause for a second. I'm going to let you think, see if you have a quick answer to that or not. So I've seen one answer in the chat, linear regression. Linear regression indeed is one way to get the logistic line. But if you wanted just a constant number out of this data, how might you get a constant number out of here? So my thought is, if I want just a constant value out of here, let me take all these PPGR values and I'm just going to average them. And I'm going to use the value for the average as the vertical component of that horizontal, the vertical height of that horizontal line. It's right there. And again, I think that's a great thing to ask students to just think about before you go on, or could you, what would you draw on here for that? So I went through with my spreadsheet. I actually used Google Sheets for this, and I calculated the United States PPGR. I got the linear regression line, that's the trend line, and I got the average value, and that's all plotted out on this graph. So those blue dots are, of course, my PPGR values at various population levels. And then, of course, you see my average is right here in red, and you see that very nice trend line coming in blue. That's for the United States data. And then if I go ahead and do the same thing for Guatemala, I just will pause for a second to give you a chance to think, what do you expect to see happen there? Or do you have just any expectations for what will happen there? So when we went ahead and did this for the Guatemala population, this is what we found. Note that we were able to get the average of the data just very fine. That's our exponential model, but we tried to do the logistic model. That trend line is actually increasing. And this actually explains why that logistic model just did not get estimated well with the Guatemala data at all. The trend line, the best fit line, is increasing and not decreasing. And that's why the Guatemala data, the logistic model, basically ended up looking like the exponential model, because the logistic model is really not an appropriate model here for this data. All right, with that, I think it is past time for me to wrap up today. So I am just going to go to my last slide. Thank you all for listening today. I did share in the chat a Google document with some resources for everyone on this, including some links to the Google Sheets that actually have the data in it. You can also fairly easily, both with my modules and with others, find the data for both the United States and for Guatemala. All right. Thank you. Does anybody have any questions that I can address before we wrap up the session today?
So Jean, you did this the entire semester, the student could finish the project and...
So when we were, we are on quarters, we're not on semesters. So we've got a 10-week quarter to work with, and generally working through with the senior student, all of the parameter estimations and whatnot, that would take a lot of the quarter, but not quite all of it. So I usually do something else on the end, although often we will actually, with the last time I taught this, I think we went and we said, okay, that trend line for Guatemala, I think I worked with actually the total global human historic population data set. That also has a trend line that increases, and we worked out the super exponential model for that. So that's a model that grows faster than exponential, which is terrifying when we're talking about the total historic global human population.
But nonetheless, it's a wonderful work. I think like you're introducing data to your students in the class and they are playing with it. They're understanding the trend and patterns. I would say wonderful choice.
Yeah.
Good to know.
I have to admit, I did not think the United States population data set and these models were all that excited when I got started, but I've now published like 3 papers on the topic with a fourth one in progress. So there's a lot more there than I have to admit that I even really perceived at first. There's also a lot of interesting tie-ins between modeling and data and then looking at what was happening historically.
Yeah, excellent. Wonderful talk.
Thank you.